So today we're going to introduce Lie groups, which is the main focus of this series of lectures. But well, it's always useful to refresh what we learned yesterday. So the most important thing we learned yesterday is what is a group. And now we all know a group is a set with a binary operator. And, okay, this is misleading. Binary operator, and we demand it to be closed. So it doesn't get out of the set. And then we demand this binary operator to be associative. And then we demand identity exists. And then we want inverse exist. So that's all. And I guess between the finite group and the continuous parameter family, we have a middle ground. So let's spend, say, 5 minutes on it, or less. So we should give an example that I have countable entries, countable infinity group, but not a continuous infinite. So. And that is hopefully something we're familiar with from growing up. That are the integers that we use all the time. Well, typically I only use 1, 2, 3, and beyond that, it's called infinity, as you also learn in the string theory class. So integers. So let's take this binary operator to be something hopefully we also learned by heart. It's called addition. So the question is, integer with addition, is it a group? Well, let's see. If I add 2 integers, I get an integer. Good. And addition is associative. I can choose which ones to add first. Identity exists. What's the identity for integer group with addition?
0.
0. Good. All right. Notation. Identity 0. Okay. We'll write it a 5. Okay. And then inverse do exist. That's how we discover the negative numbers. It's going to be a fun notation. Okay. So it's indeed a group. But if I give you 2 integers, besides adding them together, if you add the same number integer again, I can also have binary operator multiplication. Is integers with binary operator multiplication a group? No, people are shaking heads because the inverse doesn't exist. In this case, we get a 1 over 5, which is not an integer. Good. So integers. So that's why it's very confusing. You call group multiplication, because sometimes when you choose the binary operator to be multiplication, depending on which sets we're talking about, it ends up not being a group. So in order for multiplication to be the binary operator of the group, we have to enlarge the integer to the rational numbers. Okay. So a teeny bit beyond the group theory, I'm sure some people probably know way more than me, is there's something nice about the integers that we want to abstract it and see other things look like integers. And the integer has this nice property, is that it comes with the two binary operation plus and the addition and the multiplication, such that this forms even better. It forms a abelian group, in which yesterday we learned that the abelian groups are very easy to study. And for this guy, it's associative, and then it has this cute distributive property, says that I can distribute it to the members. In the parentheses, I'm sure that people are familiar with equations like this. And then they say, this basically summarizes the nice property of integers. And then they decided to call things like this a ring. So a ring is a set comes with two binary operators that forms a group with the first one, and the second one is associative and distributive. It doesn't require inverse, which integers doesn't work anyway. And the integers are probably the most well-known ring. So sometimes, or maybe you just heard from me that I call it the Lord of Rings. And if you go even further beyond that, you might also want to try to include a nice property. What if the second binary operator also have a nice property that you have inverse, you have identity, you have abelian, then you get a field. So if you ever read things as this thing over some field, then that's what they meant. Okay, so that is everything I want to say before we move on to the continuous parameters, which is the Lie group. Okay. Up to now, you should really ask me, what are we doing this besides, we're having fun with it? And they're trying to play with words and such, or drawing pretty diagrams that has been erased. These Cayley diagrams, they're always cute to draw, and they look pretty because they're symmetrical. But we should really ask, why are we learning Lie group? So far, we haven't encountered physics yet. Okay. So why should we be interested in Lie group theory, or Lie groups and the Lie algebras? This is taken from Weinberg's book, Quantum Field Theory, the really huge one, Volume 1, Chapter 2, and the section, and the subsection. So let's take quantum mechanics, for example, which in the Nature Walk talk, Barrow has revealed for us that it has a Hilbert space. So we'll start with quantum mechanics and see how group theory arises. Says that in quantum mechanics, a state is described by a cat, at least according to Dirac. And then we'll be sloppy. It should be a Rie because different states differed by some unobservable phase wouldn't be different, so we'll identify as a Rie, but I'll just write this cat. So this state, and then according to the, okay, now I have to be very careful after that talk on the pilot theory. We will use the Copenhagen interpretation, no matter how bothered it is. So we'll try to interpret the probability. So suppose, the claim is this thing is a wave function, and we can't really get physical information about it. And one of the physical information, a lot of them by the probability interpretation, is that we can calculate the probability of the state 1 goes to state 2. And this is something physics. And then this is calculated by the inner product of this thing and the modular square. And we claim this is physics. And now consider your friend who is on this moving train. There's always going to be a train. And then he's doing same experiment with some quantum system. And then you also have your friend from your home. Most of them are not from Waterloo. Probably all of you not from Waterloo. Somewhere else. They're also doing the same experiment. And you imagine that if our physics, our world is symmetric and all the physics laws are somehow we are able to learn, then we imagine that other people doing the experiment will get the same probability. So imagine some other observer will view this system from, say, psi 1 prime to goes to psi 2 prime, and then they'll come to the conclusion they have their probabilities to observe. And then, if a symmetry, it really says that this 2 probability should be invariant. And then there is a famous person, Wigner, in 30s, made the following observation. Says that suppose psi 1 prime, the second observable state, is some operator acting on psi 1, then Wigner says this operator has to belongs to, it's called the Wigner theorem. The operator can either be, has two choices. It can either be unitary and linear, or anti-unitary and antilinear. Okay, that's just what he proved. And I hope that people has reviewed the tutorial 0, then they would know what unitary and linear and anti-unitary and antilinear mean. This says if I have U psi, U phi, this will give psi and phi. And
sorry.
Yeah.
What's the? How do you derive that? Like, what are you imposing to
well, I have a very, very sloppy derivation.
Oh, sure, but I mean, it just comes from the invariance of probability, right?
Right. Yep. Yep. If you demand this probability invariant, we're going to prove that's your choice. And then there's a very sloppy way to do it. But let me just write down the definition. This says that if I have all right, I'm running out of letters. But then this says that you can, that's just what linear means. And then the antilinear just says that you pick up complex numbers, so that will equals to A star or something, and be complex conjugate things. Okay, so the reason I'm being very sloppy here is that we can make a trivial and enlightening observation, which we'll make quite a few from now on, is that identity, which is always a good operator, somehow we want to know what happens to identity. And this operator, is it a unitary and a linear, or anti-unitary and antilinear? Which one? You are giving me answer like shaking your head and pointing. No, this is a real question.
Unitary and linear?
It's unitary and linear. Very good. That's why from now on we'll only focus on unitary and linear operator, because we love something called small parameter linear approximation so much that we want to get close to identity, and this are just too far away from identity. It's not continuously infinitesimal reachable. Okay. So here comes the sloppy derivation. It's very sloppy, so bear with me. Okay, what I wanted to calculate is the probability of this guy. Okay. And then what I claim is that they are related by some operator. So it's operator per psi 1 and operator per psi 2. And then the adjoint, we can write this as the O adjoint, O per psi 2 square. And see, if I want this to be equals to the original probability, the easiest choice is just take this guy to be identity. There seems to be there are other choices should work, but that's the easiest choice. Before you take the scalar product or the modular square, they are already equal. Of course, they're equal. And that happens to describe both the unitary operator and anti-unitary operator. And the harder part is we're going to show that why all the other things doesn't work. This is actually the only thing that works. So I showed that this works. If you choose to be unitary, those two choices will preserve probability. And I think Weinberg has an appendix to reproduce or being even elaborate on Wegener's proof that why this is the only thing that works. And I would refer to the reference. So, okay, good. So we know, now we know. Now we'll focus on only the unitary operator because they're related to identity. We'll focus on them. And then now we consider there are other friends, other observers. So suppose, so now we have psi. And then we have our first friend who is on the moving train. We will observe this guy by acting a unitary operator on it. And then we'll have some other friend. So this is first observer, and then there's a second observer, and then there's a third observer. So suppose the third observer is related to the second observer by a unitary operator U2. So now we see that yesterday when Thomas pointed out my notation is not conventional. This is indeed the conventional notation is to go the other order. you act operator from the left to your state. But look, if suppose the second observer doesn't exist, only the first and the third observers exist, then they should still be related by some unitary operators, say let's say U3. So going through the second observer or not shouldn't really change anything. The third observer should observe the state be the same. And if we look at this, we see something interesting. It says one operator acts on another operator gets a third operator, and they are all in this. It looks like immensely like group multiplication. And there's this, the identity operator is chosen to be included. And you can certainly go from one observer to another observer and come back. So inverse also exists. So group theory pop out when we study quantum mechanics. So it seems that if we want to understand particles who will believe that can be described like quantum mechanics, or quantum field theory rather, we should study group theory. And well, suppose we have a Hilbert space, and even more, let's suppose it's something very convenient, like a vector space that we have knowledge about, that we can use our powerful linear algebra to study. Then the operator in quantum mechanics is normally what kind of powerful tools we use regarding operators that act on vector space. No?
Linear maps?
Linear maps. Good. And very good. So if we have linear maps, and then normally we will use something that has columns and rows. So normally we'll use matrix to acting on vector space, and acting on vector and getting other vector. So normally when we write this down, that we use matrices to study them. So the next topic would be group representation. There are lots of abstract groups relating rotating oranges and Rubik's Cube and such. And then it's nice if we can study all the groups using only one language. Here, yes.
So what were you saying about U3, U2, and U1? Because they don't necessarily form a group, right? So then what were you saying about the relevance of group theory?
Well, why don't they necessarily form a group?
It's like applying U1 over and over again takes you outside of those three elements.
Oh, right. Sorry. So there's going to be many of them.
Or do you mean like the group of?
Like the group of all, the group of all the operators related to all the observers you can imagine. Okay. Yeah, you're right. It's of course not just these three operators. It's like all the operators related to, say, the symmetry of the Minkowski space. Yep.
But I didn't quite understand the argument that you said about them being invertible.
Well, if what I'm saying is that psi, so this guy is equals to the operator acting on psi. But you can imagine that if this must be something acting U1 psi by must get back to psi. There must exist such operator because there should be symmetry between the two observers. No.
Okay.
Look, if I'm a person standing here doing my experiment and there's another person like running at 1 meter per second and doing the experiment, we can always consider he's doing the experiment at rest, and then we should be, if there exists an operator bring my state to his state, there should be some operator bring his state to my state.
Okay.
Since we are all equal observers. Okay, so what? So let's look at the group representations. Group representation says we have a set G, well, the group G, and it has many elements. And soon enough, I wouldn't be able to list them this way. But since I haven't got a Lie group yet, I can still write down all the elements. And then the idea is we can actually represent all the groups using matrices. So for each element, and then we're given, say, a matrix as a function of this element, which, let's say, it's a square matrix with m dimensions. Well, of course, we shouldn't just assign random matrix to the group. Then we'll lose the fact that it's a group. So we want these guys to preserve the group structure. Which is to say that we have all these matrices, and they follow the rule that if element A multiply B gives us A multiply B, then after you map them into these matrices, then the matrices should also have this group structure. Then we say, okay, that's actually all the group it is. Now we can discard wherever the group is coming from and only study the matrices. Well, actually, you would say study even more stuff, because you can find tons of representation of the group. Like for one group, it could have many, many, many representations. But once you get into the regime of the matrices, you have the powerful tool of linear algebra to do whatever you want. Okay, let me emphasize that these matrices don't have to be distinctive. You could have assigned one matrices to multiple group member. So that's allowed. For example, I can be silly, say, give me a group, very good, I will assign identity matrix to all your group members. That's certainly a representation. And they certainly preserve the group structure by the fact that the identity matrix times identity matrix equals identity matrix. But it's not very useful. If you say every group is just a bunch of identity matrices, then we lost quite a bit of the interesting group structure. But it is allowed. So those are called the unfaithful representation. And the faithful representation will require them to be distinctive. So we're only interested in the faithful representation, which get all the truths out of the group. And in parentheses, we say there is always the trivial representation using identity matrix only, but it's, of course, unfaithful and not very interesting. Okay. And then, you can represent your groups in many ways, but beware, some of your representations might be the same in disguise. So this is coming to this is related to what is called a similar transformation of matrix. Says that A is similar to B if A and B is related to by a similar matrix transformation. So if I can find S such that A and B are related this way, then we call A and B are similar. So it's possible I have if representation D and D prime are related by a similar transformation as such then we claim these two representations are similar and they are equivalent. So this is because so that should be for any group member, this is true. If for every group member, the two representation is related to by a similar transformation, then we say, well, these two representations can be studied together as an equivalent class. Yes?
Is S the same for all?
Right, S would be the same.
The same for all group elements? Okay.
Yeah. Because that's why we say, well, that we do demand it to be the same because we can look at the group representation equation says that the A, so A should preserve the group structure, and indeed, if they are related by such similar matrices, and the thing in the middle will cancel.
The minus ones on the other side.
Right, that doesn't make sense. Thank you. Okay, so we do require data the same as for all of them. But then they say that as long as it works for two group, for the, say, the generators, because of this holds, then it holds for everything else.
Should that be a D prime numberized?
There should be a D. Thank you. Yep. So then we say, okay, then they are indeed similar, and we should consider them equivalent. In other way, we can consider that the similar matrix representation says the only thing you did is you use some linear transformation to scramble up your vector space. So your vector space, you have chosen some different bases for your vector space. And that really didn't affect your operators. You can still consider your operators are the same. That's why that we say, you have equivalent group representations, and then we shall be only interested in the inequivalent one. We are only interested in faithful ones, and they should be inequivalent. We're only interested in particular equivalent class of group representations. And then furthermore, that because of this similar transformation, sometimes you will say this is possible if there exists some particular transformation that could bring your matrix representation in a block diagonal form. So this is possible. that you assign each group member a matrix, but sometimes you can use this similar transformation to make them all look like this. And then it's 0 unless it's in this diagonal boxes. So, and then this, if this is possible, which I don't know actually how people actually do it to find this, as it's gotta be hard, because it's gonna be a really big dimension matrix, and you want to survey all the matrix S to bring it into this form. But it's possible sometimes, and then the representation is called reducible. And of course, if it is impossible, no matter what you do, there's always it's never look like a block diagonal. It will be called the irreducible representation. As you see, in some particular choice of this equivalent class, there exists one representation that looks block diagonal, which means we can just consider all the vector space a direct sum of each other, and each little block only act on a few entry of the vector space. So they are basically decoupled. And there is no interest of studying, say, this giant matrix, which takes more time to study, if we can focus on each individual block. So further, so what we are only interested in faithful, irreducible, equivalent class of group representation. So, what's the use of this thing? Well, it is very useful that after 2 classes, we'll get back to this, actually focus on finding all the irreducible representation. For example, you might have heard of SU2 is the group of spin. So you could have spin half particle, spin 1 particle, spin 3 half particle, and then you see each of them are irreducible representation, and then we can study it separately. So for example, if you find aliens who are using different language, and you really want to communicate, it says there is a very important particle called an electron with this alien. And then you say this electron, weighs 511 K electrovolts. But they are from America, so they weigh it with pounds or potatoes. So I still think that, if you can weigh things with pounds, you might as well use potatoes or root paca or whatever root vegetables. So this weight of electron doesn't make any sense to some alien that it doesn't, weigh things the same way as we do. But you can always say, oh look, this electron. It is a 2-dimension representation of some group. And maybe the alien would realize, oh, you're talking about that spin 1 half particle, which is an electron. All right, so we'll definitely come back to the representation. And as things, as more concrete things instead of just blobs showing up, and it will become more enlightening. But for now, we'll say that this is going to be our focus. But now it's a good question to ask. In particular, this class, which kind of Lie group would interested in? Right. Okay. Before we ask which, we should ask what. What are Lie groups? Well, Lie groups are basically groups that I can't count, So we shouldn't even label it with any index that run through integers. And the only thing we can do is to label them with continuous parameters. So be a group. It's still a group, but the group members are labeled by continuous parameter. Say theta. So we'll use this notation and make a tutor to say it's a tupelet, that it could have many continuous parameters. It's just a notation. And then, as usual, we should start with one continuous parameter. Which we can relate this group as I have a plane, and now I rotated by some theta angle. And this theta that relates all sort of rotations on one plane would indeed form a group. So for example, we can see this group is called e to the I theta, with theta go from 0 to pi, I guess. But it's a continuous parameter. And you can verify that e to the I theta 1 times e to the I theta 2 will give you something also look like a member of group. So it's closed. The identity exists, which is when theta equals 0. And then the inverse exists, which is when theta goes to minus theta. And of course, it's associative because it ends up to be addition of angles. So this is very good. Then we also realize this group has this very nice property, is that it's commutative. Well, then we immediately lost interest because abelian groups are easy to study. So that's how much we're going to talk about that group, which has a cute name called U1. That will come back why it's called U1. But it's abelian, it's a group. Okay. We decide to move on. So remember when I count, I decide to count from 1, 2, 3, and infinity. So we have studied the rotation in the plane. So the next, of course, we're going to study rotation in 3 dimensions. So how many continuous parameters is rotation in 3 dimensions is going to have? Okay, so there is the xy plane, so I can rotate that way. And then there is the xz plane, so I guess I rotate this way. And then there is the yz plane. No, this is the xz, yz plane, so I rotate this way. So rotations in 3D will be described by 3 parameters, which corresponds to the rotation in yz plane, the rotation in the x plane, and then the rotation in xy plane. Okay? And then we can also try to write down these rotations, and then to show that it also form a group, which probably it does. Here's a question. Suppose I take out of these rotations in 3D, I take just the rotation in the yz plane as we studied it before. Then that would be a subgroup. And now the question is is rotation restricted in one plane a normal subgroup of rotation in 3 dimensions? Well,
No.
no.
If there were rotations with commute. If there were rotations in different places with commute, and they don't.
They will. And yes, you're right. The rotations in this is actually not a normal subgroup. So you can actually take another element, such as, say, 0, pi over 2, and 0, some rotation in other plane, and you can calculate the cosets, and then realize the cosets, this coset doesn't exist, cannot be achieved by any coset from the left. So you can actually prove the 2 sets of left and right cosets do not agree. Okay, that's just a review from what we have yesterday. What else do I want to say about the rotations in 3D? Well, not much. So let's generalize to rotations in d dimensions. Right? It's the game. We studied 2, 3, and hence we can study anything. Okay, so now let's come to the linear algebra, our very effective tool of study things. So let's write this rotation in 3D more formally. Formally, I meant that suppose in d dimension I have a vector x. Then, if I choose some orthonormal basis, I should be able to write it as the linear combination of the basis with some coefficient and normally called the coordinates. People should all be familiar with Einstein convention. So if index are repeated, they are sum. So there has a sum here, but normally nobody writes it. Okay. So if I have a vector, and you will always say people will define an inner product on this vector space, which is the normal inner product. You just multiply the coordinates together. And by this definition, we can calculate the norm of this guy, which is given by calculating the inner product with itself and take the square root. Okay, so now we can define the rotation in general. Rotation is the operator brings a vector into a different vector such that the norm is preserved, or the inner product is preserved. So we will have, which kind of looks like the probability things we're talking about, that we demand the inner product is preserved. That's what we call a rotation. If you rotate a vector, the length doesn't change. And actually, the angle doesn't change either, and thus the inner product doesn't change. So if this is what we demand, we will get that. And hence we conclude rotations should satisfy the condition of R transpose times R equals identity. Yes?
I just have a question about before. Why do you need 3 parameters to describe rotation in 3D when you can make the third one out of the first 2? Right? Like,
how do you make the first?
isn't like you can set up like you can rotate like this, and that's the same as going like this. You know, like it's like the same as saying that you can
Right.
make the third like angular momentum operator out of the first 2.
You're right. You are saying that.
So like that's a reducible like that would lead to a reducible representation, or something.
No, the SO3 indeed have a 3D. It has 3 real parameters, and it does have a 2D representation, but it has a 3D representation. I think the thing, what we are thinking about is more like we can describe a point on the sphere with 2 Euler angles.
Yeah.
Right.
Okay, kind of like that.
Right, kind of that way. But think about it, it's a rigid body. So it's not just a point, but it's like a object. Then the object, besides you have to use 2 angles to describe where the object is, it needs another angle to describe what the object itself rotates.
Okay.
So that's the 3 angles. Yeah.
And Alan, in some sort of way, if you have, you can have the third angle, it's about the third rotation between the 2, composing 2 rotations, but that element, the composition, should be itself another element in the group, so it should be there already without talking it as a composition.
Yeah.
So you need the third angle.
Okay.
Think about 2 parameters, like one being the normal, the unitary normal, and the other one the rotation of the
Yeah.
For example, you have this.
Okay. All right. Thanks.
Okay. So as I say that if we use the linear algebra and the matrices, the vector space, to define the rotations as things that preserve the length of the vector and the angles between the vector, then we obtain this matrix equation, which doesn't refer to the dimension, and hence is generalized to in any dimension. Question?
I don't know. It's good answer.
Okay. So this is the rotational group, also called the orthogonal group. So normally it's defined, which is written as ON. Well, if you are familiar with the language Mathematica, you begin to not like the idea of using n as a variable, because Mathematica doesn't allow you to do it. So normally, I'll write a number in it, and that's how you discover there's a group called the no group. But that's our orthogonal group. So the thing we really cared about a group, see, Lie group, when you ask, so the thing we care about a group yesterday is giving me a group, I wonder, hey, how many elements are there? And if they are 12 and 24, you begin to think, maybe there's a subgroup, maybe I can use direct product, semi-direct product, da-da-da-da. But if you give me Lie group, you ask, how many elements? Yeah, infinite. Then we should somehow be able to compare some Lie groups are more complicated than the others. And that's why we care about the number of the real parameters. And I confidently claim that O3, the rotations in 3 dimensions, must be more complicated than rotation in 2 dimensions because I need 2 more parameters. Yep.
Just to be clear, when you say rotation group, do you mean reflections as well?
I do mean the reflections as well.
Oh.
Right. So you meant, so for example, this element? Right. The minus infinity is included at this point. We'll get rid of it because we always care about the ones connected to identity. what I said is whenever we're given a Lie group, a first interesting question is how many real parameters are there to describe this Lie group. Well, we know that for 2 we have 1, for 3 we have 3. So for n we have, I guess that's not a very big set of mapping. So for the orthogonal group, you actually have 2 approaches. And the first approach is the same as we have already used in the 3D, right? In 3D, we say for every 2 plane, you can rotate around that 2 plane. So that should work in higher dimension. I can't draw it for you and I can't imagine it for you. So I'm not a mathematician. If you ask a mathematician, says, how do you imagine a 60 space the Calabi lives in? Mathematician says, that's simple. I first imagine it's n dimension, and then I take n equals 6. But let's say for any of this n dimension, I should be consistent. For any n-dimensional space, I can always project it down to some 2 plane. And in this 2 plane, I'll be able to write down a real parameter to describe rotation on that plane. And so how many parameters I need?
Combinatory number n2.
Right. N choose 2, which is n minus 1 divided by 2. Okay. This is a very good approach. It gave me a number, says that the rotations in n dimensions should give us this many real parameters. But this approach is when we still have some idea about rotations in 2 planes and such. So let's also introduce the other approach. So the second approach says I can count all the parameters and subtract the constraints I have. Okay. So given an n by n matrix, I certainly have n square parameters before I put any constraint on it. And now I have a constraint. And this constraint is very interesting because this constraint, I can transpose this constraint. Man, it gives me the same thing. So which means that this, you would think this gives me n square equations, but since it's the same as its transpose, so those constraints are symmetric, right? Because it says it equals to its transpose. So there are n square equations, but only the upper triangle matters. So the number of this constraint is how many entries are there in the upper half of the matrix, which is n times n plus 1 divided by 2.
So can you repeat the argument about the transpose?
Right. So you have n square equations.
Sure.
And if the transpose of this n square equations equals itself, it means, so I have n square equations. And if the transpose of the equal self says this equation is actually the same as this equation, and this equation is the same as this equation. So the independent equations are only the upper half. Yep, question.
Was the argument that the rest are actually independent?
What's your, well, that's the only constraint we impose. Oh, okay. You're asking, given this, why the rest are independent? Well, it didn't have constraints on them. Like I can't find any way to relate those equations. Like this doesn't impose any relationship on the rest of the equations. So they should be independent. Yeah.
For example, your determinant has to be 1 of your matrix. That's an equation. That's a constraint. Or -1 out of it.
All -1.
Yeah.
That's taken into account
that's
in our theory equals.
What?
That's already taken into account in our theory equals 1.
But you don't have n times n plus 1 divided by 2 free parameters.
We don't.
Yeah, then
what you just said.
We're getting a different conclusion.
We're getting rid of them. Those are the constraints, and we have this many parameters, subtract this many constraints, and we will reach this. Okay, but your question gives it already been asked, is the reflection included? And now the question about determinant comes up. So we should emphasize this. So if we look at this matrices, so the question is the determinant equals 1 plus 1 independent, another equation on top of this equation? And the answer is no. And you can take the determinant of this equation. And then the determinant of R transpose is the same as determinant R. So we get to the conclusion the determinant of R is either +1 or -1. And since we already emphasize a lot, we only care about the things that are close to identity matrix. So there we claim that if your rotation has determined R equals +1, this matrices are special. And that's why we discovered the special orthogonal group, which only focus on the matrices that has determined equals +1. Question?
So I think you might be skipping a step in the parameter counting there, because so that transpose thing just says that like the orthogonal group is like closed under transpose. It doesn't like give you any relationship between the matrix and its transpose. So I think you're counting the parameters in the Lie algebra there, which is like the same dimension, right? Like, so that parameter counting holds for when you have like the relation that like R transpose equals minus R or something, right?
R transpose equals.
Oh wait, never mind. Okay, you're subtracting. Never mind.
What?
Never mind.
Okay. The only thing this argument is saying that if R has n entries, R has n square entries, and R transpose has n square entries, and then this equation should have n square equations. And the only thing I'm saying is that some of these equations are nothing but repeating the equations you already write down. And we shouldn't contain the two equations that look exactly the same as if they are different. So we should subtract away the equations that are repeating. So in this particular sense, when we have some intuition, the geometry approach of just counting how many two planes there are more appealing. Because when all your equations are somehow not independent, then you have to think about which of them are independent and then subtract them. And the reason this approach is introduced is because there is some other group that we have no idea about the two planes and such, and this approach is much easier. But what I want to emphasize is that for the special orthogonal group SON, what's the number of parameters?
It's the same.
It's the same. You have a group and you say, well, throw half of it away. Then it doesn't change the continuous parameter count. You still need this many continuous parameters. And since you might be getting this question from the interview, let's box this important number. Okay. So that's that. And then I want to just mention this special group called SO31. So what I have been saying so far is on the Euclidean space, which some steps has been skipped, or some other things has been skipped, is that we have a 1, 1, 1, 1, 1 metric, and this rotation, this rotation actually preserves the metric too. And then if we use a acute metric that has a negative entry, and this is our Minkowski space, you can still define rotation on them in the same way, except your inner product will be defined with this eta mu nu that has negative entries. And this is an important group that it has 6 real parameters. Okay, so this is the familiar 3 rotations and the 3 boosts. Okay, so the last thing we want to mention is, besides the rotations in n dimensions, we also want to talk about rotations in complex dimensions. What I meant is just doing exactly the same thing, except now we allow the matrix entries to be complex. So it's just directly taking the R transpose R equals identity. Now we want to study U dagger U equals identity, and then all the U's also form a group. And this is known as the unitary group, which is of great importance in the future. Okay, and again, once we're given a group, a Lie group, we always want to count the number of parameters. And this I have no intuition whatsoever how to count the parameters. So I will follow this recipe. So it's how many parameters I have, real parameters we have, because it's an n by n matrix that is a complex, so I started with 2n squared. And for this equation, that all the equations are independent, so we just subtract n squared, and it says we have n squared parameters left. Okay, and again, we are interested in the group that is close to the identity, or in other words, that since it has a abelian subgroup, and we're not interested in abelian subgroup, we want to quotient away somehow. So again, we look at the determinant of this equation. And now, this one has not just 1 plus minus 1 as solution. Now it has the U1 as solution. So your determinant can be anything that has modulo 1. But nevertheless, we decide to claim if it's plus 1, then it's special. In this way, we can divide this U1 subgroup away, and we obtain the special unitary group, SUN. In this process, look that we indeed lost a continuous real parameter. So for special unitary group, the number of parameters is n squared minus 1. And this is an important count you want to know. And why the special unitary group is important? Well, we'll get to know that in 2 lectures. And it's basically, SU2 is the simplest Lie group that is non-abelian to study. It has the simplest structure constant, and the most important of all, we can find all the irreducible representation, which you can know as the spin n half particles. Okay, the final remark. Okay, let's write down the important knowledge from this class. Is the SON is described by n times n minus 1 divided by 2. And SUN has number of parameter n squared minus 1. And that's the most important thing to remember from this class. And we'll come back to structure constant tomorrow. But I want to point out this fun fact is that 3 times 2 divided by 2 is 3, which is also equals 2 squared minus 1. So the number of parameters describing SO3, which is the 3-dimensional rotational group that is close to identity, just divide the reflection out, is somehow curiously the same as the special unitary group that with 2 by 2 unitary matrices. This curious fact you will find out in the Friday's tutorial, that you can actually construct maps that to say one of them is the double cover of the other one, hence they have the same number of real parameters. And you can continue this called arithmetic fun fact study and realize that SO4 has 6 parameters, which is curiously equals to 3 plus 3. And the fun fact about this, you might have heard about the SO31, known as the Lorentz group, the group of the Minkowski space, have a double spinor representation. So that curious fun fact will be reviewed at the last lecture when we attempt to classify all Lie groups. Then you would realize this is really a direct sum of 2 SU2s. And the last fun fact is that tomorrow's tutorial, we'll look at this thing at an intensity that you might not like, or you might like. It's a very gory intensity of this Poincaré group, which is really saying the Lorentz group that has 6 parameters and the translations in R4. So this way, this one has 10 parameters. And tomorrow you will see the glory details of how to find out all the structure constants, all the Lie algebra of Poincaré group. According to Freddy Casasso, everybody should do that calculation once. It's not that hard, but it has a lot of index manipulation. Okay, so I guess we're done.